Right now, at the center of our galaxy, there is something that weighs 4 million times more than our sun. It doesn't shine. It doesn't reflect light. It occupies a region of space smaller than our solar system, and yet its gravitational influence shapes the orbits of stars moving at thousands of kilometers per second. For decades, we assumed objects like this were cosmic dead ends, places where matter goes to die, where physics itself breaks down, where nothing interesting could possibly happen because nothing can escape. But here's what's strange. When astronomers finally turned their most powerful instruments toward these objects, they didn't find silence. They found something far more unsettling. Black holes, it turns out, are not quiet. They are among the most active, most luminous, most violent engines in the entire universe. Some of them are responsible for the very existence of the galaxies they inhabit. Some of them may have shaped the conditions for life itself. And some of them appear to be doing something that, according to our best understanding of physics, should be completely impossible. This is not the story you were told about black holes. This is the story of what they actually do. You will not go back to the moment they were first predicted, because even that story is more surprising than most people realize. Black holes were not discovered through observation. They were discovered through mathematics, almost by accident, by a soldier sitting in the trenches of World War I. In 1915, Albert Einstein published his general theory of relativity, a radical reimagining of gravity not as a force, but as the curvature of space and time caused by mass. Within months, a German physicist named Karl Schwarzschild, serving on the Eastern Front, found an exact solution to Einstein's field equations. His solution described what would happen if you compressed a mass into an infinitely small point. The geometry of space-time around that point would warp so severely that nothing, not even light, could escape beyond a certain distance. That boundary became known as the event horizon, and the object itself became known eventually as a black hole. But here's the remarkable part. Almost nobody, including Einstein himself, believed such a thing could actually exist. Mathematics allowed it. Nature, they assumed, would not. Surely, they thought, some unknown force would prevent matter from collapsing so completely. Surely the universe had safeguards against such extremes. For decades, black holes remained a mathematical curiosity, an elegant but uncomfortable prediction that most physicists preferred to ignore. Then, the universe began sending signals that were very difficult to explain any other way. In the 1960s, astronomers discovered objects at the edges of the observable universe that were astonishingly bright. They called them quasars, quasi-stellar radio sources, because they looked like stars but emitted far more energy than any star possibly could. A single quasar could outshine an entire galaxy of hundreds of billions of stars. The energy output was staggering, and it was coming from a region of space no larger than our solar system. No known physical process could account for this. Nuclear fusion, the engine that powers stars, was nowhere near efficient enough. Chemical energy was laughable at these scales. The only mechanism that could generate such extraordinary luminosity from such a compact region was gravity itself, and not just any gravitational process. It had to be matter falling towards something extraordinarily dense, something with an event horizon. Slowly, reluctantly, the scientific community began to accept that black holes were not merely theoretical. They were real, and they were doing something no one had anticipated. They were feeding. When matter falls toward a black hole, it doesn't simply drop straight in. Because of angular momentum, it spirals inward, forming a swirling disk of gas and dust called an accretion disk. Think of it like water circling a drain, but at velocities approaching the speed of light. As the material spirals closer, it compresses, it heats up. Friction between particles in the disk generates temperatures of millions, sometimes billions of degrees. At these temperatures, matter radiates furiously across the electromagnetic spectrum, from radio waves to visible light to X-rays. The accretion disk around a supermassive black hole can convert roughly 10% of the mass energy of infalling material into radiation. To put that in perspective, nuclear fusion in the core of our Sun converts less than 1%. Black holes, the darkest objects in the universe, are paradoxically responsible for some of the brightest phenomena ever observed. The thing that lets nothing out is surrounded by the most luminous light show in the cosmos. This was the first great surprise. But it was not the last. As astronomers mapped more and more galaxies, a peculiar pattern began to emerge. Nearly every large galaxy appeared to harbor a supermassive black hole at its center. Not a small one, not a modest one. These black holes contained millions to billions of solar masses. Our own Milky Way has one, called Sagittarius A, weighing around 4 million solar masses. The galaxy M87 has one weighing 6.5 billion, and the largest ones we've found tip the scales at over 40 billion times the mass of our Sun. But the truly puzzling discovery was not the black holes themselves. It was the relationship between these black holes and the galaxies surrounding them. Astronomers noticed that the mass of the central black hole was tightly correlated with the mass and velocity dispersion of the galaxy's central bulge of stars. The bigger the bulge, the bigger the black hole. And this relationship held across wildly different types of galaxies, across different sizes, different ages, different environments. This was deeply strange. A supermassive black hole, despite its enormous mass, is tiny compared to its host galaxy. Sagittarius A, for instance, weighs 4 million solar masses, but the Milky Way contains roughly 1 trillion solar masses. The black hole is less than 1/millionth of the galaxy's total mass. Its direct gravitational influence extends only a few light-years, while the galaxy spans 100,000. How could something so comparatively small be so intimately connected to something so vast? It would be like discovering that the size of a city's central fountain precisely predicted the population of the entire metropolitan area. There had to be a hidden connection, a feedback mechanism linking the growth of the black hole to the evolution of the galaxy itself. And this is where the secret life of black holes truly begin. When a black hole is actively accreting matter, it doesn't just emit light. In many cases, it launches enormous jets of magnetized plasma that shoot outward from its poles at nearly the speed of light. These jets can extend for hundreds of thousands of light years, far beyond the boundaries of the galaxy itself, plowing into the surrounding intergalactic medium like cosmic fire hoses. The energy carried by these jets is almost incomprehensible. They heat the gas around the galaxy, pushing it outward, preventing it from cooling and collapsing to form new stars. Imagine a city's water supply being controlled by a tiny valve at the very center. Open the valve, and the city flourishes. Close it, and growth stops. The black hole, through its jets and radiation, acts as that valve. When it feeds aggressively, it heats and disperses the raw material for star formation. When it quiets down, gas can cool again, drift inward, and eventually trigger another feeding episode. This creates a self-regulating cycle, a cosmic thermostat that controls the growth of the galaxy over billions of years. The black hole and the galaxy are not separate entities. They are a coupled system, evolving together, each shaping the other in a gravitational and energetic dance that spans cosmic time. This idea, known as active galactic nucleus feedback, or AGN feedback, has transformed our understanding of galaxy evolution. Before its discovery, computer simulations of galaxy formation had a serious problem. They consistently produced galaxies that were far too massive, with far too many stars, especially at the high mass end. The simulations couldn't reproduce the universe we actually observe. Something was missing, some mechanism that suppressed star formation in the largest galaxies. When researchers added black hole feedback to their models, the results suddenly matched observations. The galaxies came out the right size. The star formation rates looked correct. The mass distribution across the universe aligned with what telescopes were showing us. The secret ingredient, the missing piece of the cosmic recipe, was the black hole. Not as a passive gravitational sinkhole, but as an active participant in shaping the large-scale structure of the universe. But this raises a question that cuts even deeper. If black holes regulate galaxy growth, and galaxies provide the environment for star systems and planets and ultimately life, then in some indirect but very real sense, the existence of supermassive black holes may be a prerequisite for our own existence. Without them, galaxies might have converted all their gas into stars too quickly, burning through their fuel in a cosmic instant, leaving no raw material for the slow, patient chemistry that builds rocky planets and organic molecules. The black hole, by throttling the rate of star formation, may have given the universe the time it needed to produce complexity. This is a stunning inversion of the popular image. The black hole is not the destroyer. It is, in a sense, the regulator, the governor, the quiet hand that slowed things down just enough for the universe to become interesting. And yet, even this picture is incomplete, because there is a chapter in the life of black holes that remains genuinely mysterious. A chapter that takes us to the very edge of known physics. In 1974, Stephen Hawking proposed something that seemed almost heretical. Using the principles of quantum mechanics applied to the curved space-time near an event horizon, he showed that black holes should not be perfectly black. They should emit a faint glow of thermal radiation, now known as Hawking radiation. The mechanism is rooted in one of the strangest features of quantum theory. The vacuum of space is not truly empty. It seethes with pairs of virtual particles that flicker in and out of existence. Near the event horizon, Hawking argued it is possible for one particle of a pair to fall into the black hole while the other escapes. The escaping particle carries away a tiny amount of energy, and since energy and mass are equivalent, the black hole loses a corresponding tiny amount of mass. Over unimaginably long timescales, this process would cause the black hole to shrink, to evaporate, and eventually to vanish entirely in a final burst of radiation. This idea, beautiful as it is, creates one of the deepest paradoxes in all of physics, the information paradox. When matter falls into a black hole, it carries information with it, the quantum states of every particle, a complete physical description of whatever was consumed. If the black hole eventually evaporates entirely through Hawking radiation, and if that radiation is purely thermal, meaning it carries no information about what fell in, then information has been destroyed. But quantum mechanics has a fundamental principle: information is never truly lost. The evolution of quantum states is always reversible, at least in principle. You should always be able to reconstruct the past from the present. If black hole evaporation destroys information, then either quantum mechanics is wrong, or general relativity is wrong, or our understanding of both is incomplete in some profound way. This paradox has consumed theoretical physics for nearly half a century. Some of the most brilliant minds of our time have worked on it. Various proposals have been put forward. Perhaps information is encoded on the event horizon in a way we don't yet understand. A concept related to the holographic principle, which suggests that all the information contained within a volume of space can be represented as data on its boundary. Perhaps there are subtle correlations in the Hawking radiation that encode the information, invisible to any simple measurement but present in the full quantum state. Perhaps there are remnants, tiny Planck-scale objects left behind when the black hole finishes evaporating, carrying the missing information within them. Perhaps the event horizon is not the smooth, featureless boundary that general relativity predicts, but instead a seething firewall of high-energy particles that destroys anything crossing it, which would violate a different fundamental principle of general relativity known as the equivalence principle. None of these proposals are fully satisfactory. Each solves one problem while creating another. The information paradox remains open, and many physicists believe that resolving it will require a complete theory of quantum gravity, a framework that unifies general relativity and quantum mechanics into a single coherent description of nature. Black holes, by their very nature, are the places where these two pillars of modern physics collide most violently. They are the laboratories where the next great revolution in physics may be born. And the mysteries do not end there. Consider this. We have observed supermassive black holes that existed when the universe was less than 1 billion years old. The quasar J0313-Wade806, for example, hosts a black hole of roughly 1.6 billion solar masses, and its light comes from a time when the universe was only 670 million years old. How does a black hole grow so massive so quickly? If black holes grow by accreting matter, there is a natural speed limit called the Eddington limit. Beyond a certain rate of infall, the radiation pressure from the accretion disk itself pushes incoming material away, choking the black hole's food supply. Even accreting at the maximum Eddington rate continuously since the Big Bang, It is very difficult to grow a black hole to 1 billion solar masses in under 1 billion years, especially if you start from a stellar mass seed, the remnant of a massive star's death. So where did these early monsters come from? Several theories have been proposed. Perhaps the first black holes formed not from individual stars, but from the direct collapse of enormous primordial gas clouds, skipping the stellar phase entirely and producing black hole seeds of tens of thousands or even hundreds of thousands of solar masses right from the start. Perhaps mergers between smaller black holes in the dense early universe accelerated growth beyond what accretion alone could achieve. Perhaps the Eddington limit can be exceeded under certain conditions, through geometrically thick accretion flows, or through episodic super-Eddington feeding. Perhaps the seeds were even more exotic, remnants of phase transitions in the early universe, or collapsed products of dark matter halos. We do not yet know. The existence of these early supermassive black holes is one of the outstanding puzzles in modern astrophysics, and the James Webb Space Telescope, now peering deeper into the early universe than any instrument before it, is already finding more of them, earlier than expected, in greater numbers than our models predicted. There is also a mystery closer to home, a gap in our black hole census that has only recently begun to be filled. We know about stellar mass black holes, typically between 5 and 100 solar masses, formed when massive stars collapse at the end of their lives. And we know about supermassive black holes, millions to billions of solar masses sitting at the centers of galaxies. But what about the middle? Where are the intermediate mass black holes, those weighing thousands to hundreds of thousands of solar masses? For years, these were the missing link in black hole astrophysics. Without them, it was difficult to construct a plausible growth history connecting stellar remnants to supermassive giants. Recently, gravitational wave observatories like LIGO and Virgo have begun detecting mergers that produce black holes in this intermediate range. The detection in 2019 of a merger producing a black hole of roughly 142 solar masses was the first direct evidence of an intermediate mass black hole, and observations of certain dense star clusters and dwarf galaxies have hinted at black holes in the range of thousands to tens of thousands of solar masses. The picture is slowly coming into focus, but there is still so much we cannot see. And this leads to perhaps the most humbling realization of all. Black holes, by definition, hide their interiors from us. The event horizon is not a physical surface. It is a boundary of knowledge, a point beyond which no information can reach us, no signal can escape, no measurement can be made. Whatever happens inside a black hole is, in the most fundamental sense, unknowable to an outside observer. We can write equations that describe what might happen. General relativity predicts that matter falling past the event horizon will inevitably be drawn toward the singularity, a point of infinite density where the curvature of space-time becomes infinite and our equations cease to make sense. But whether the singularity actually exists, whether it is a point or a ring or something our mathematics cannot yet describe, whether it represents a true breakdown of physical law or merely a breakdown of our current theories, these are questions we cannot answer from the outside. The interior of a black hole may be the most real and most inaccessible place in the universe. Some theorists have speculated that the singularity is replaced by something else entirely. Perhaps quantum gravity effects prevent the collapse from proceeding all the way to infinite density, creating instead a region of extraordinarily but finitely curved space-time. A Planck star or a quantum bounce that might, on unimaginably long timescales, explode back outward. Perhaps the interior of a black hole connects to another region of space-time, not through the science fiction wormholes of popular imagination, but through some yet unknown geometric structure predicted by a complete theory of quantum gravity. These ideas are speculative, but they are not idle. They are driven by the deep conviction, held by many physicists, that nature does not tolerate true infinities, that whenever our equations produce an infinity, it is a signal not of physical reality but of our own ignorance, a signpost marking the boundary of what we currently understand. What we can say with confidence is this: black holes are not the simple cosmic vacuum cleaners of popular myth. They are dynamic, evolving, deeply connected objects that shape the galaxies around them, regulate the birth rate of stars, emit radiation through quantum processes that challenge our deepest physical theories, and serve as the ultimate testing ground for our understanding of space, time, matter, and information. They are simultaneously the most extreme predictions of general relativity and the most compelling evidence that general relativity itself must eventually be replaced by something deeper. And here is what strikes me as the most extraordinary thing about this entire story. We live in a universe where the darkest objects are responsible for the brightest lights, where the most destructive forces may be necessary for creation, where the places we can never look inside may hold the answers to questions we have been asking for centuries. Black holes are not the end of physics. They are its frontier. Every observation we make, every signal we detect, every equation we write brings us a little closer to understanding what they truly are. But with every answer comes a new question, and the questions keep getting deeper. The next time you look up at the night sky, consider this. At the heart of the soft glow of the Milky Way, hidden behind clouds of gas and dust, there's a region of space-time where 4 million suns worth of matter has been compressed beyond the point of no return. It has been there for billions of years. It helped shape the galaxy you live in. It may have played a role in creating the conditions for your existence. And it is keeping secrets that we are only just beginning to learn how to ask about. The universe, it seems, hides its most profound truths in the darkest places. And maybe that is the deepest lesson of all. That the things we cannot see are sometimes the very things that make everything else possible. We are only at the beginning of understanding the secret life of black holes. And the secrets, it turns out, are far stranger and far more beautiful than the darkness ever suggested.